Hello, and welcome to Group 5's presentation on high performance concrete. A brief history of ultra high performance concrete. First developed in France by employees of a French contractor, Buoys, in 1990s. Released on the public market by a French company, Lafuge Cement Company, under the trade name Ductile. Official application uses was in Canada on a bridge. Properties of three different types of special concretes: self-consolidating concrete, high-performance concrete, and fiber-reinforced concrete. The three of them overlap, and that's what makes up ultra-high-performance concrete. Over here, um, you have your normal concrete, your high-performance concrete, and then your ultra-high-performance concrete right next to each other, and that's 20 millimeters going across diameter of each of those cross sections. And you can see the difference in the size of the material that is going into these different types of concretes. And of course, like most concrete, we have sand, cement, water. The main things that are different in ultra high performance concrete is the silica flume, the superplasticizer, and the steel fibers. The silica fumes, they fill in the smaller spaces and kind of bond around those objects that normally you wouldn't have anything in. The plasticizers um, actually help reduce the amount of water so that you can have less water in the actual cement. And then, of course, the steel fibers, um, which happens to be the most common type of fiber that's used in ultra high performance concrete. Okay, so another thing that super plasticizer that does is it allows things to flow, which allows the concrete with the silica flume and the steel fibers to be extremely dense and flow into cracks that it normally would not flow into. Okay, so now those fibers that what I was talking about, the most common are steel fibers. There are two different types, though, of steel fibers that most people use in high performance concrete. Not all, but the majority of professionals use is the macro and the micro steel fibers. The macro includes things like these twisted steel fibers and the waved steel fibers. And then, of course, the micros you can see are quite a bit smaller than the macros. Um, and if you can see the ruler here, this is 1 centimeter. So it's the micro steel fibers are not much more than a centimeter long. And most of the test results that we're going to review today are going to be on steel fibers because they're the most commonly used type of fibers. But there are other types of fibers that can be used in high performance concrete. Some of those alternative fibers are polyurethane fibers, glass fibers. When we say glass, we're thinking of like fiberglass type fibers, and then synthetic fibers, usually like a nylon. And then you have like natural fibers. When you think natural fibers, think cotton, bamboo, those type of natural fibers that can be found in the environment or grown in the environment. So, some of the main characteristics of ultra high performance concrete is the fact that it has unbelievable strength and unbelievable flex abilities. Um, and you look at the traditional concrete and you've got maybe 20 to 40 MPa compression, which isn't bad. It's that's pretty good. But then you have this unbelievably strong ultra high performance concrete would be its strength and its flexibility. When I say flexibility, I mean its ability to actually flex. So the test results from one of my many sources tested the difference between macro and micro steel fibers resulted in you see on this page. And that would be the strength, the compression test. It withstood 124 to 160 megapascals with the macro steel. That would be the twisted and the waved version. And then the micro steel fiber ultra high performance concrete was able to withstand 135 to 170 micropascals before failure. The other thing was the flex test. And this lovely photo over here is actually a picture of their actual setup for the flex test. Flex test with the macro steel fibers was between 9.5 and 23.7 macropascals before failure. for the ultra high performance concrete. And for the micro steel fibers, in the ultra high performance concrete, it was 17 to 34.2 MPAs before failure, which is unbelievable and pretty amazing. And that's really awesome, really cool characteristics that the ultra high performance concrete does have. So the last two things that I want to add to its main characteristics that most people don't think about is the fact that it has amazing impact and blast resistancy. And that's due to its denseness and its really low permeability and porosity. Its fractal energy is about 250 times that of ordinary concrete, which means it can absorb a much higher level of impact before it actually fails, which is absolutely ideal when you're looking at something that needs to be able to withstand seismic activity and absorb an impact. The other thing that it has that it's amazing that most people don't really think about is its electrical resistancy. Your traditional concrete has about a 24, where your ultra high performance concrete has over 480 uh, KUM, KUCM resistancy. And it has a charge transference of about 48 coulombs in comparison to your traditional concrete has 5,148 coulombs transfer, which means when you're looking at that, it's the transfer of vibration from through it. So like if something hits it, what comes out the other side, um, which is pretty amazing. So it literally absorbs that impact instead of transferring it, making it ideal for blast situations or impact situations, which is very unique to it. I think those are the main components that I really wanted to hit on that.
What are the common applications of UHPC? UHPC has a great potential to be a practical solution to improve the sustainability of buildings and other infrastructure components. UHPC is utilized in architectural features, repair and rehabilitation projects, as well as vertical components such as windmill towers and utility towers in the oil and gas industry. UHPC applications, bridges. Roads and bridges are the most popular application of UHPC. The most common bridge application are field cast UHPC connections. This image is of the Route 23 bridge located in Wanata, New York. Field cast UHPC connectors were utilized during its construction between precast concrete deck panels. The UHPC eliminates the conflict between the reinforcement bars and other connectors, allowing for easy field assembly. UHPC applications offshore structures. Offshore platforms are subject to complex environmental loads and chemical erosion, which makes them an ideal candidate for UHPC use. Due to its remarkable mechanical properties and durability, UHPC facilitates advancements in offshore engineering structures with low maintenance costs and ease of construction. The use of UHPC in floating wind turbine foundations has extended the service life of the structures. UHPC improves the durability and performance of wind load and wind load resistance. UHPC is currently being utilized in the Southern Power Grid Gyujen offshore wind farm, which is responsible for delivering green and clean wind energy to the Zhuhai power grid in China, seen above. Offshore platforms are also beginning to integrate UHPC. Here we see the Norway's Troll A platform. Due to its position, the platform is subject to seawater corrosion and frequent freeze-thaw cycles, and the use of UHPC in key structural joints has enhanced the durability and sustainability of the structure, improving its safety and service life. UHPC applications, harbor structures. Like in offshore environments, harbor structures need to withstand erosion from seawater and immense mechanical loads. Ports, docks, and harbors are among the structures that are starting to incorporate UHPC in everyday construction. UHPC was utilized in the terminal upgrades done at the Port Hamburg in Germany, seen at the top. The port is situated at the mouth of the Elbe River in the North Sea. The river is significantly affected by tides, meaning the water level changes frequently, and the North Sea is notorious for extreme weather and strong waves. UHPC was chosen for its low permeability, high density, and resistance to corrosion. Breakwaters are another common application of UHPC due to its inherent need to withstand strong wave impacts. Breakwaters are constructed to protect port facilities and surrounding communities. Following the 3/11 tsunami disaster in Japan, a breakwater rehabilitation project was started in Kashimi Harbor. UHPC was used in wave dissipation blocks and revetment panels because of its high strength and mechanical properties in extreme conditions, seen below. UHPC applications tunnels. High population in dense modern cities has driven the need for exploration of underground construction. Utility tunnels are another application being explored for UHPC. Utility tunnels house and protect water supply, electric power, gas, telecommunication lines, sewage, and etc. UHPC is used in a three-part system along with engineered cementous composition and ordinary concrete. UHPC is used as an exterior layer to protect the tunnel from water penetration and corrosive agents in the soil, while ECC is used as an interior layer to improve crack control and fire resistance. Ordinary concrete is utilized to fill the space between the two layers to minimize the thickness of the other two layers.
Hello, everyone. My name is Devin Kanopka, and I'll be going over UHPC from an owner's perspective, and specifically why many agencies are choosing UHPC, even though it comes with higher upfront costs. The biggest reason is durability. UHPC costs more per cubic yard, but it lasts significantly longer and performs better in aggressive environments. So for owners dealing with bridges, marine structures, or anywhere exposed to chlorides, freestyle cycles, and heavy wear, UHPC becomes a long-term investment rather than just a material choice. I want to make sure to emphasize that UHPC is expensive up front, but the durability difference is huge, and that's what drives its adoption. On this slide, we're looking at durability performance, and you can see why UHPC stands out. UHPC typically shows 5 to 10 times better durability than normal concrete, and that's across multiple durability mechanisms such as chloride penetration, freestyle damage, abrasion, scaling, and the overall deterioration. Even without numbers being shown, you can clearly see that UHPC consistently outperforms traditional mixtures. This is why you see UHPC used heavily in coastal states, cold climates, and structures that can't afford frequent maintenance. This slide highlights why UHPC performs the way it does. The key difference is the microstructure. UHPC is designed with an extremely dense particle packing and a very low water to cementous ratio. That creates a microstructure with very low pore connectivity, which is what prevents water, the chlorides, and other harmful agents from moving through the material. Normal concrete has a network of connected capillary pores, while UHPC almost entirely eliminates that, which makes this the foundation for all the durability advantages that we just talked about. Another big contributor to durability is the crack control. UHPC doesn't just have higher strength. The cracks that do form stay incredibly tight, typically under 0.05 millimeters. The steel fibers disperse throughout the mix and help bridge micro cracks, preventing them from opening wider. And that's crucial because the wide cracks are what allow water and chlorides to enter and start the corrosion process. UHPC cracks are so small that they don't create those pathways at all. A key thing to remember is that UHPC protects itself by controlling the cracks before they become a durability problem. Here we have a real service life comparison. The charts on the right will show deterioration trends from conventional concrete versus UHPC. Traditional concrete may start showing significant scaling damage at around 20 to 40 years, depending on the exposure, while UHPC maintains its integrity for far longer, typically projecting 100 to 150 years of service life. This is the moment where you really understand why owners are willing to pay more for UHPC up front because you're trading a slightly higher material cost for essentially doubling the lifespan of the structure. So upfront versus long-term value. This is where the cost discussion gets put into perspective. Standard concrete might be around $120 to $150 per cubic yard, while UHPC often ranges from 1,000 to 2,000 per cubic yard, depending on the proprietary mix. So yes, UHPC requires a big upfront investment, but because the material is so dense and uses steel fibers, silica fumes, and other fine powders, that cost reflects the specialized nature of the mix. When you combine that with the reduced deterioration over time, the long-term value becomes very clear. So why is it cost effective? Even though UHPC costs more initially, owners save money over the life of the structure. This is mostly done through the things below. Minimal maintenance, UHPC doesn't just deteriorate the same way traditional concrete does. There's fewer and smaller repairs, no major patching, less scaling, and no significant cracking. And also reduced closures, meaning fewer disruptions to traffic and other operations. The photos on the right show UHPC being placed in one, a repair overlay, and then two on a bridge deck, which are the two of the most common applications where agencies see huge long-term savings. So the key takeaway is UHPC may be expensive up front, but for structures expected to last 75 to 100 plus years, it is often the most economical option over the full life cycle.
What are the limitations and negativities associated with using UHPC in construction? Well, ultra high performance concrete is a type of advanced concrete that has very high compressive strength, tensile strength, excellent durability, and strong resistance to environmental damage. It is often used in bridges, high rise buildings, facade panels, and other infrastructure projects where long service life and structural performance are important. Despite these advantages, UHPC has several limitations and challenges that need to be considered during design, production, and construction. So, as you look over here at my image of this high rise ish building, it's a 5-story building, but on the sides, you can tell that this is concrete that wraps all the way around this building that holds the building together, not only together, but also holds this cool architectural design on the side, which looks to be steel holding on the side of the building. So when you're driving in the building, they don't fall on you and crush your car and maybe a person. But also, as you can see in the parking garage, we have these pillars holding the building up, which are made out of UHPC. But not only are these holding up the building, you have concrete footings that wrap around this whole building that help support this building so it doesn't come crashing down on top. So at number one, we have cost material consideration. UHPC is much more expensive than regular concrete. It's sometimes 3 to 10 times more expensive, and that's due to fibers, high cement content, and special mixtures. Also, it's limited availability at standard ready mix plants. It usually requires custom production. And UHPC also requires precise mixing and strict quality control to ensure consistent performance. So, as you can see in this image, these are the special concrete mixers to be able to produce this UHPC, and I'll get more into them in the next slide, but as you can tell, these do not look cheap. So next we have placement and construction challenges. Dense mix can be difficult to place. Large pours may require special pumping equipment. There's also high shrinkage during curing, which can cause early cracking if not managed properly. Which you can see right here that there's some cracking, so someone did not do their job correctly and it caused cracking. But it's pretty much due to the high shrinkage and it wasn't cured properly. And last, we have often needs steam curing or controlled environments to reach full strength and durability. So on the left side, we have the full strength and durability right here of the UHPC. That's what it should look like. And right here is when it doesn't cure properly and it starts to crack. Third, we have design and labor consideration, limited building codes and standards for UHPC. Engineers often rely on project-specific guidelines and testing. Skilled labor is needed for proper handling, placement, and curing. Fiber distribution must be even, or it can reduce tensile strength and ductility, which will lead to cracking. As you can see in this image, we have a crew of some experienced concrete workers. This guy's holding the pump line, pumping in concrete. This guy's raking in concrete in the holes, trying to spread it evenly. You got a guy right here. Alexa, turn on the light.
Okay.
You got a guy right here holding some rebar. I'm sorry about that, by the way. Holding rebar. Then you got a guy back here. Looks like he's raking in concrete and missing holes as well. Then we come to environmental and practical limitations. UHPC leaves a higher carbon footprint compared to regular concrete due to large cement and additive content. We have extremely strong and dense, making it hard to cut, modify, or demolish after curing. So once you pour it, it's going to be very hard to cut it, change the look of it, like move it, anything like that. And then when you come back to destroy it or demolish it, it's also going to be harder to do that as well. So this requires careful planning to make sure benefits outweigh the cost and construction challenges. So on the right side, I found this little chart. It's like an environmental impact assessment for UHPC. There's a global warming potential, acidification of land and water. You got human toxicity, formation of tropospheric ozone, and depletion of non-renewable resources. So, as you can tell, there's a few limitations and negativities that come environmentally with using UHPC. Last, we have our works cited page for our whole entire group. And that is it. Thank you.